Hello. We've already looked at how we can use some simple substitutions to find integrals or antiderivatives. Now we're going to look at how substitution can help us in some slightly more complicated situations where we maybe have to do a couple of different substitution type things. So let's look first off at, we have x times the square root of 3x plus 4 dx. Now, if I think, okay, well, I want to make u equal the argument inside the radical, the radicand, and that is what you want to do here. But that doesn't fully help me. So let's do that basic substitution here. Du would be 3 dx. Or in other words, in order to replace the dx, I'm going to need to replace it with 1/3 du. But if I just do this substitution as is, I've still got that x out there. So x times u to the 1/2 times 1/3 du. So I also need to substitute that x. Well, according to this substitution, x is equal to, let's go, u over 3 minus 4 over 3. So it's a binomial. So it doesn't seem to be making this more doable if I'm going to have to substitute that, but it actually does. And the reason it does is because it's fine to have the binomial with no exponent. What's tricky is having a binomial with an exponent, particularly where that exponent is rational. So 3x plus 4 to the power of 1/2 is harder to deal with than u over 3 minus 4 over 3. So let's actually substitute this last bit in as well. So now what we have is, I'm going to put the 1/3 out front, u over 3 minus 4 over 3, u 1/2 du. And in fact, actually, I can factor out another third, so I have 1/9 out front, just to not deal with the fractions here. U minus 4, u 1/2 du. The reason this helps is because now I can actually distribute this multiplication so that I can just use the power rule. So this is 1/9 u to the power of 3/2 minus 4u to the power of 1/2 du. So using the power rule, I get 1/9 times u to the power of 5/2 divided by 5/2, which ends up being the same as multiplying by 2/5, minus 4 times u to the power of 3/2 divided by 3/2, which ends up being the same as multiplying by 2/3. So I end up with this, plus some constant. And I'm going to call it C1 for the moment because I'm not quite done here. Distributing out, so I'm going to distribute the 1/9 back through, and I'm going to replace u with 3x plus 4 again. So I have 5 times 3x plus 4 to the power of 5 over 2, all over now 18, minus 8 times 3x plus 4 to the power of 3 over 2, all over 27. And I'm just going to say plus c now. This is a new constant. I took the original constant and multiplied it by 1/9, but it's still just a constant. So I don't have to write c over 9. I can just write c. And that is the antiderivative of the given function. This is an indefinite integral, so I end up with a function, and I'm not given an initial condition, so I have to have the plus c. Let's look at what happens if I do substitution with a definite integral. And again, a slightly more complicated substitution, but as a general rule, I'm going to want to make my substitution the argument of whatever more complicated function. So here I have to the power of 1/2, so I'm going to make that equal u. So u equals 1 plus x cubed. Now we have something where du is actually more than just a numerical coefficient of dx. So du equals 3x squared dx. So in order to replace dx, I'm actually going to write this as 1/3 du equals x squared dx. Because I do have sort of an extra x squared here. This is actually x cubed times x squared. So I can use this x squared with the dx. And I have an extra x cubed. But I can replace that extra x cubed because x cubed is equal to u minus 1. So now what I have is the integral of, okay, so I've got a 1/3 coefficient out front. I've got u minus 1 replacing the x cubed. I've got u to the power of 1/2 replacing the 1 plus x cubed to the power of 1/2. And x squared dx is being replaced with the du, the 1/3 I've already written. The other thing that I want to change is I actually want to change the upper and lower limits. So I'm not going to have to substitute back in for x if I change the limits of the definite integral. So if x equals 0, then u equals 1. If x equals 2, then u equals 9, because it's x cubed plus 1. So my new limits on my definite integral are 1 to 9, and I don't have to substitute back in for x before I substitute in the values. So one last bit of cleaning up, and that is to distribute the u to the 1/2. So I now have u to the 3/2 minus u to the 1/2 du. So now I can antiderive. So I get 1/3 times u to the power of 5/2 divided by 5/2, which is the same as multiplying by 2/5, minus u to the power of 3/2 divided by 3/2, which is the same as multiplying by 2/3. I don't need to worry about a constant because this is definite integration from 1 to 9. And finally, I do my substitution. So 1/3 of 2 times 9 to the power of 5/2 over 5 minus 2 times 9 to the power of 3/2 over 3 minus 2 times 1 to the power of 5/2 over 5 minus 2 times 1 to the power of 3/2 over 3. So just to kind of finish this up, this is 2/5 minus 2/3. Square root of 9 is 3. 3 to the power of 5 is, I want to say 243, but I am going to check that. It is 243. So 243 times 2 is 486 over 5. And so we've got 27, so this one is just 18. Yes, okay. So when I simplify that, 486 over 5 minus 18 minus 2 over 5 plus 2/3, and that all gets multiplied by 1/3. What we end up with here in the final accounting, I believe, is 1192 over 45. Now I've done that fairly quickly, so please feel free to check my work and let me know if it is incorrect. But I believe that will be the definition, the definite integral here. And then the final example we're going to do, again, a slightly different format. It's not given to me in the integral format, and it is an indefinite integral here. I'm finding a function, but I have an initial condition, so I will be able to figure out the value of c. So I'm going to separate this. I get dy equals x over x plus 1 dx, which means that I can integrate both sides. So I get y equals the integral of x over x plus 1 dx. In these scenarios where you have a denominator here, a very, very useful substitution is to substitute u for the denominator. So u equals x plus 1, which means du just equals dx. And the numerator, therefore, x is going to be u minus 1. Again, it's more helpful to have a binomial in the numerator than in the denominator, because then I can distribute. So what I have here is now that y equals u minus 1 over u du. Again, this is helpful because now I can distribute. So this is 1 minus 1 over u du. Once I've distributed, I can integrate. So the antiderivative of 1 with respect to u is just u. The antiderivative of 1 over u is the natural log, and it's actually the natural log of the absolute value of u, plus some constant. Again, I don't have u, I have x. So x plus 1 minus the natural log of x plus 1 plus some constant. But I know that when x equals 0, y equals 6. So 6 equals 0 plus 1 minus the natural log of 0 plus 1 plus c. So the natural log of 1 is just 0. So this bit right here is 0. So we have 0 plus 1 plus 0, so in other words, just 1, which I subtract, so 5 equals C. So what we end up with as our final function is that y equals, jumped a little, y equals x plus 1 minus the natural log of x, absolute value of x plus 1, plus 5. And that is the specific function that satisfies these conditions. So there you have it, 3 examples of slightly different scenarios where we can use substitution to make our lives a little easier.